photodiode. Okay, so little introduction about the photodiode. Again, we are going about so this photodiode introduction and structure and working principle, advantages and disadvantages we'll discuss today. Okay. First of all, photodiode. A photodiode is a light-sensitive electronic device capable of converting light into a voltage or current. That means this photodiode is so it converts the photodiode into optical energy to electrical energy. So electrical energy means in the form of voltage or current. If when light is instant on the this diode, when light is instant on this diode, that light is absorbed by this diode, and that absorbed light is converted into electrical energy. So that electrical energy is in the form of voltage or current. Okay. Now it works on the principle of photo generation. It works on the principle of photo generation. So already we know that what is the generation. Generation means so to break the covalent bond. Okay, so when we supply the photon to the semiconducting material, that semiconducting material absorbed that energy, and covalent bond of the that semiconducting material will breaks. Okay, so if covalent bond will breaks means what happen? Electron hole pair will be generated. Electron hole pair will be generated. So that is absorption of the photon. What happened here? Electron hole pair is generated. That's why this is called as photo generation. Photo generation. So that's why. So because of that, what happened? So electron hole pairs. What happened here? Current, either current will be produced, or so we can observe some voltage here. Okay, so that is called as here optical energy is converted into electrical energy. So that's why simply we say that it works on the principle of photo generation. Okay, next the symbol of photodiode is shown in below figure here. So this is the p region and this is the n region. Okay, so p region is connected to anode, and this is connected to the cathode here. Okay, n region is connected to the cathode. Okay, so this is the overall diagram of the PNG photodiode. Okay, I will explain this briefly. Okay, in next diagram. Here semiconductor photodiode is a reverse biased PN junction diode. So this is connected as a reverse bias. Reverse bias means P terminal is connected to the N region and N terminal is connected to the positive. So positive terminal is connected to the N region. Negative terminal is connected to the P region. Okay. So then it is called as reverse biased. Reverse biased. Okay. The structure of photodiode is shown there. Here this is the structure is given. So inside metal substrate will be there, and here N layer will be there. So on that N layer, P layer is deposited. Again on the P layer, so there are two metal contacts will be there. So in between there is a gap. That gap we will call it as window. That gap we will call it as window. Okay, so through this window what happen? Light will enter into the diode. Light will enter into the diode. Okay, so in P region, especially in P region, so there is a two contacts will be there. So two metal contacts on each edge. So this side edge and this side edge. So metal contacts will be there. So through the metal contacts you can supply the power. Okay, in between those two metal contacts there is a gap will be there. That gap we will call it as window. Okay, yeah. So this is the circuit diagram. Yeah, here terminals are given wrong. See here. Can you observe? So this is the P region, this is the N region. But in case of photodiode, it should be in reverse bias. But so this is connected as forward bias. This diagram is wrong here. Okay, this is so we have to see. So this is the positive terminal we have to connect here. Okay, so now if it will be, so this is the positive terminal and this is the negative terminal. So negative terminal is connected to the P region and positive terminal is connected to the N region. Okay, now structure. So structure of the PN, this diode, photodiode. Structure of the photodiode here. So now first N-type layer is grown on the substrate, and P-type layer is grown on it by the process of diffusion. Okay, first of all we will take any substrate, that maximum, that is the metal substrate. Okay, we will take the metal substrate. On that metal substrate, N region will be, first of all N region will be grown. So how it will grown means, so by using physical vapor deposition or chemical vapor deposition, so we can deposit the material. We can deposit the material on substrate. That deposited material will be grown like a layer on the substrate. Okay, so by using diffusion process it will be grown. Okay, next next of all, on the N layer, P layer will be deposited, and this layer also grown on the N layer. P layer will be grown on the N layer. So in between, because of and what is the reason for growing means here? So because of the diffusion process. So because of the diffusion process, what happened? So this P region is grown on the N layer. So because of that diffusion, what happened here? There is a junction will be formed. Junction will be formed in that N and P region. N and P region. That junction we will call it as depulsion layer. That junction we will call it as depulsion layer. Okay, and here, so there is a window will be there. So through that window, light will be entered into the this diode. Yeah. So now one more thing here. Two ohmic contacts are made at the P and N type semiconductor, in which one ohmic contact act as a anode while other act as a cathode. Already we discussed which is the anode, which is the cathode. So here for the N region, so one metal contact is connected. For P region, another metal contact is connected here. Okay, these will be act as a anode and cathode. By using these contacts, we can supply the power. We can supply the voltage. Okay. Now coming to the next point, the ohmic contact connected to the P region in such a way that it allows the light to fall on the device as shown in, yeah. So here, so that means, see here. So in P region, the ohmic contacts will be there. Those are connected on the only edges. Okay. So there is a gap will be there. That gap we will call it as window. Through that window, so light will be enter into the instant on the diode. Light will be enter into the diode or instant on the diode. Okay, so this is now coming to the working. So above one is the structure. Now working of the photodiode. So working of the photodiode is based on the internal photoelectric effect. Already we discussed about there are two types of photoelectric effect will be there. One is the internal photoelectric effect, another one is the external photoelectric effect. Okay, so this photodiode is worked based on the internal photoelectric effect. Based on the internal photoelectric effect. So what is the definition of internal photoelectric effect? Means free charge carriers are generated by absorption of incident photons in semiconductor injection detectors. Okay, when light is instant on the semiconducting materials, what happened? Already we discussed that covalent bond will be breaks. So because of that breaking of covalent bond, electron hole pair will be generated. Okay, electrons will be present in the valence band and holes will move to the conduction band. Holes will be present in the valence band and electron will move to the conduction band. Okay, so these are the charge carriers. So those charge carriers are freely move inside the material. Okay, so this effect we will call it as this effect. When light is instant on the semiconducting material, electron holes pair will be generated. So those electron hole pairs will be move freely inside the material. Okay, that is called as internal photoelectric effect. Okay, now the diode is connected in reverse biased under the instant photons. Okay, here diode is connected in reverse bias. Okay, now free charge carriers are created by the photon absorption. So whenever photon is absorbed, so whenever light is instant on that junction diode, photon will be absorbed. If photon is absorbed means free charge carriers will be developed. Okay, so that is the point here. The pair of electron hole is generated. So already we discussed every single instant photon. If for each single photon, if diode will works accurately means, So for that, each photon involving in a electron hole pair generation. Each photon involving a electron hole pair generation. Okay. So at that only efficiency of the diode will be very high. Responsibility also very high. Okay. Now these moving charge causes current flow through the external circuit. Here what happened here, so electron hole pair will be generated. Those are the charge carriers. So those charge carriers will move freely. That's why. So these are involving a circuit flow. So in that, so because of those carriers, what happened? Current flow through this circuit. Current flow through this circuit. Okay. Now coming to the, yeah, see here. So negative, this is reverse bias connection. Negative terminal is connected to the P region and positive terminal is connected to the N region. So there is some resistor will be there. So by using that resistor, so this is the load resistor. So by using this resistor, so we can get the output voltage. You can get the output voltage. Okay. Now coming to the reverse bias photodiode is under luminescence. So luminance is nothing but incident photons. So E is represented the energy band gap diagram in below figure. Okay, here energy band gap diagram is so represented. See here, this is the energy band gap diagram. This is the P region and this is the N region here. Okay, so see here. So whenever light will be instant on, the diode, what happened? So it will be so this is the region. What is the depulsion region? So that the energy is light energy is absorbed by this depulsion region. In that depulsion region, so covalent bond will breaks and electron hole pair will be generated. Electron will come like this and hole will be in valency band. Okay, so which absorbed in the junction via window. So already I said that window is nothing but in P region there will be a gap will be there. That gap is window. So through that window light will be reaches to the junction. The absorbed energy rises a bond electron across the band gap from the valency band to the conduction band. Okay, so here whenever light will be instant on the junction, what happen? Electron hole pair will be occurs. That means here bond will breaks, covalent bond will breaks. So electron hole pair will be generated. So electron will be present in the valency band, hole will be present in the conduction band. Now what we are doing here, so this is connected in reverse bias. That means P region is connected to the negative terminal and N region is connected to the reverse bias. We are connecting here reverse bias. If you connect the reverse bias means what happened? So these positive P region is connected to the negative terminal. That's why. So these positive charge carriers moves towards to the P region. Similarly, so these negative charge carriers move towards to the positive terminal. These negative charge carriers moves towards to the positive terminal. So that's why because of these charge carriers here. So holes and electrons will be present at the junction. So because of these charge carriers, what happened? Current flow through this circuit. If you connect in a reverse bias. Okay. Now coming to the concept of photodiode as a photodetector. See here. Optical excitation leads to increase in the reverse biased current. So if you intensity of optical signal will increases. That means power of the optical signal is increases. What happen? So current also increases. If intensity will be increases means so more number of covalent bond will be breaks and more number of electron hole pair will be generated. Okay, so these will act as a minority charge carriers. Okay, because of these minority charge carriers here, so current is passing in a reverse bias. Okay, so now observe here. Suppose if you connect this diode in forward bias, means what happen means, so already we know that at the junction, so if you connect the PN junction in forward bias at the junction, so electron will recombine with the hole. So that's why photon will be emitted. That means if you connected it in, it means so it will act as a LED. It will connect the diode in a forward bias, means it act as a LED. Okay, in case of photodiode, we are connecting in a reverse bias. Reverse bias. Okay, if you connect reverse bias, means width of the depulsion layer will be increases. Width of the depulsion layer will be increases. So that's why. So there is a more gap for light instanting. Okay, so that means width of the depulsion layer will be more, means so there is a more light will be fall on that. More light will be fall on that depulsion region. More light will be fall on the depulsion region, and so more electron hole pairs will be generated. More electron hole pair will be generated, and current also high. Okay, see here, we will observe that. So first of all, so dark current. If you observe the IV characteristics of the this photodiode, IV characteristics of the photodiode. Okay, so first of all, so we will observe this line. So this is the dark current. Dark current is nothing but without instanting any light. So if you will take a photodiode, so we are not light is not instanting on that photodiode. Okay, there is no light instant on the photodiode. At that time also there will be a current will be there. There will be a current will be there. So what is the reason for current? So it will be act as a like PN junction diode connected in a reverse bias. If you connect the PN junction in reverse bias, what happens? So due to itself there are some minority charge carriers will be there. Itself there are some, that if you will take PN junction diode itself, there are some minority charge carriers will be there in N region. So there are minority charge carriers are holes. In P region, minority charge carriers are electrons. So due to that minority charge carriers, little amount of current flowing through this circuit. See here, that scale also in microamps. Microamps means this current will be very small. This current will be very small. Okay, now without applying any light, there is a little flow of current in the diode. There is a little flow of current in the diode. That current we will call it as dark current. Without applying any external photon. Okay, that means without absorption of any instant light. Some current is passing through the diode. That current is called as dark current. Now, with increasing the intensity of light. So if you increase the intensity of light, what happens? So number of photons will be, so more number of photons will be instant on that photodiode. So if you increase the intensity of light, what happens? More number of photons will be instant on that photodiode, and more number of photons are absorbed by the photodiode, and because of that absorption, more electron hole pair will be generated. So more electron hole pair will be generated means there are more charge carriers. That's why so current also increases. See here. So if you will take intensity 10,000, okay, so 10,000 okay, per meter square. If you will take so luminescence per meter square, this is LM. Okay, lumen for meter square. Okay, if you will take LM for meter square, so 10,000 LM for meter square means here current will be so 100 microamps. If you increase the intensity 15,000, so LM for meter square. So here, so current will be 200 microamps. Okay, similarly if you will take 20,000, okay, if you increase the intensity, what happens? So current also increases. If you increase the intensity of the light, so current also increases like that. So we can also measure the intensity of the light also. By using this photodiode, we can also measure the intensity of the light also. So how much light is instanting on. Okay, if it will be very less intensity means current will be less, high intensity means current will be more. So this already we know that this current is called as reverse saturation current without applying any light absorption. That means without any absorption of light. So initially there is a current flow through the circuit, flow through the diode. So that current we will call it as dark current. Okay, now so that these IV characteristics. So IV characteristics of the photodiode similar to the PN junction reverse bias characteristics. characteristics. So if you observe the PN junction, so PN junction diode, so there will be a PN junction diode characteristics, forward bias and reverse bias. If you will take, so the characteristics diagram will be on three regions. So one region will be, so if you will take, so one region will be on third coordinate, another region will be on fourth coordinate. So next region will be on first coordinate. So that means in case of forward bias, that is a first coordinate. Okay, some at lower voltages. So we also observe the, so that diagram in third coordinate also. If you will take photodiode, so IV characteristics of the photodiode will be only on the third coordinate. Okay, this is the IV characteristics of the photodiode. Okay, now, so already you know that what is the use of photodiode. It will be used as a photodetector. It will be depends on the intensity. Okay, intensity means if intensity will be high means, so more current will be passing through the circuit. Intensity will be less means less current passing through the circuit. And so frequency also, it also depends on the frequency also. Frequency means if there is a certain particular frequency, so frequency is less than the energy gap. There is no current, only dark current will passing. So dark current means that is initially inbuilt in the diode. Initially, due to the minority charge carriers of the P region and N region, so some current is passing that. So that is the dark current. If frequency is less than the energy band gap of the semiconductor, so there is no excess current passing through the circuit, only dark current will pass. Okay, that's why by using this diode, frequency also we can frequency response also we can calculate. Okay, so is it less frequency is there, more frequency is there, so by using that we can calculate. So that's why, so here there are some advantages will be there. So first one is the better frequency response. So if it will be high frequency, more than EG, so it will be responded. Less than energy gap, it will not respond. Okay, and so this is a linear. So if you observe the curve means, so this curve will be like a linear curve. If you observe the characteristics means, so that current, so voltage versus current. If you observe the voltage versus current curve, so that will be a linear curve. And less noise. If you will take the PN junction photodiode, there is a noise is very less. Okay, it can be used as a variable resistance device. So how it will be used as a variable resistance device means, see here, if you increase the intensity of the light, so what happens, resistance of the diode will be reduces. That's why, so we can treat it as this is a variable resistance. Okay, so at initial cases resistance will be very high. If you increase the intensity, so that resistance will be decreases. Because more current is passing means resistance will be decreasing. Okay, so that's why, so it will be used as a variable resistance devices. It is highly sensitive to the light. If you little variation in the light intensity also, so current will varies. If there is a little variation in intensity also, current will be varies. That's why this is highly sensitive to the light. And the speed of operation is very high. It will be operated very fastly. The switching of current and hence resistance value from the high to low. Otherwise, it is very quick. Okay, we discussed. So current is increases. Very suddenly with increasing the intensity of light. Similarly, so resistance also decreases. with increasing the intensity of light. Similarly, so if you reduce the intensity of light, so what happens? Current is reduces as well as so resistance is increases. It is a very quickly process. Okay, so these are the some advantages of photodiode. Okay, now so there is some disadvantages also there. So we'll discuss those disadvantages. Small active area. small active area means if you will take the, see here, this junction. So this is junction, this is P region and this is the N region. So if you observe that, so this is the junction. This junction area is very small. This junction area is very small. Okay, so that's why. So what happened? So so if you will take very high intensity is not possible. So there is a particular limit of intensity and there is a particular limit of absorption of light, because area of absorption is very small. Area of absorption is very small. Okay, so that's why because of this that means compared to the forward bias, so it will be, so width is little high, but so it will be area also very small. The depositional area is also very small, approximately in micrometers only. That area width of the deposition layer will be in micrometer size only. Okay, so that's why, so that area of the deposition layer also very small. Okay, so that's why mainly what is the reason why here more area is required means, so electron hole pairs will be generated. That means light is absorbed in this region only. Light is absorbed in this region only, and electron hole pairs will be generated in this region only. Okay, that's why. So in case of, if you take normal PN junction photodiode, so this width of the deposition layer will be small. Okay, and next point, rapid increase in dark current, and it depends on the temperature. So already we know that what is that IV characteristics of the PN junction diode. So this PN junction diode also, this diode characteristics, photodiode characteristics also same as a PN junction diode, same as a PN junction diode. So in case of PN junction diode, we observe that if you increase the temperature, if you increase the temperature of the diode, what happens? So current also increases very suddenly. Current also increases very suddenly. Okay, so that's why here, so dark current will be increases. Dark current means here, so this is the dark current. So dark current means without involvement of photon, some current is emitting here. Without involvement of photon, some current is emitting. That current is, we will call it as dark current here. Okay, that dark current with increasing the temperature, what happens? So number of charge carriers, minority charge carriers will be increases. Minority charge carriers will be increases. Okay, so that's why current automatically increases with increasing the temperature. With increasing the temperature. So that's why, so there is a, we will little confuse in between the, so this current is due to the temperature or this current is due to the photon. We don't know exactly. Okay, so that's why, so we should always maintain the constant temperature. We should always maintain the constant temperature. That is the very little difficult process. Okay, so always maintaining constant temperature means, so it is a little difficult process. That's why, so this is the one disadvantage here. With increasing the temperature, what happened? Dark current increases very rapidly. Dark current increases very rapidly. So that's why we have to control the temperature. So controlling of the temperature is very difficult. Very difficult. Okay. Now require the amplification at low illumination level. Okay. So suppose here, so very less intensity is instant on. Less intensity is instant on means here approximately 10,000 will be there. So 10,000 lumens per meter square. Okay, suppose that will be 100 lumen per meter square. So at that situation, so it will be approximately just nearer to the dark current. That current is approximately just nearer to the dark current. Okay, that's why what happened? So we cannot detect the change of the current. We cannot detect the change of the current. More accurate ammeters are required. More accurate ammeters are required. Okay, so for detecting the little changes, for detecting the, so here if you observe here, so if you increase the 5,000 lumens, just 100 microamps current is increases. Microamps current. See here, microamps means very small current is increases. If you increase the 5,000 lumens of the intensity, so what happens? Just 100 microamps current is increases. Okay, that means if you will take very less intensity, less intensity, so we cannot detect that change of current. That change of, so initially dark current will be there. So if you increase the little amount of current, increase the sorry, if you increase the very small intensity will be increase means, so that current increase is very small. We cannot detect that. That's why, see here. That's why for observing that very low intensity currents, so we need some amplification is required. So amplification is required. So that means that increased current we have to enhance further. So that's why we have to use the amplifier, current amplifiers we have to use. Okay, and next point is photodiode characteristics are temperature dependent and have poor temperature stability. Already we discussed. So it will be, so photodiode characteristics are temperature dependent, so and poor temperature stability. That means always maintaining the constant temperature is very difficult, because whenever light is instant on the photon, so whenever light is instant on the diode, what happened? So that some light is absorbed, diode is absorbed that photon, and covalent bond will break. So in that situation, so not only emitting the light, some heat also produces. Okay, so that means all energy is not converted as a light energy. So all absorbed energy is not converted as a light energy. So there is a, so some heat energy also produces. Because of that heat energy, what happened? So that diode energy will be increases. So whenever, so continuously light is instant on that diode. Suppose continuously some light is instant on that diode. What happened after certain time? So the diode temperature will be increases. So that's why what happened? So the characteristics of the diode will be changes. The characteristics of the photodiode will be changes. Okay, because the characteristics will be temperature dependent. If you increase a little temperature also, what happened? Current will be increases very drastically. So that's why, so this is the one disadvantage. And next one is current change in current is small and hence may not be sufficient to drive the circuit. Okay, so change in current is very small. So current passing through the circuit or change in current is very small, hence may not be sufficient to drive the circuit. Okay, by using this current we cannot run the circuits, we cannot drive the circuits. Okay, because this current is very small. So by using this current we cannot drive the circuit, hence amplification is necessary. In photodiode based circuit. So that's why we should use the current amplifiers. So amplification is compulsory. So far, if you use the photodiodes. Okay, because so change in current is very small, as well as current passing through the circuit also very small. So already we observe that. Okay, how much current is passing here? How much current is passing here? Very small amount of current, just 100 microamps. For, so 10,000 lumen per meter square. 10,000 lumen per meter square. Okay, so that's why, so this is very small current. So if you want, so by using this current we cannot drive the circuit. That's why amplification is necessary in photodiode based circuit. Okay, so this is about the some disadvantages. Okay, so for overcome the disadvantages in PN photodiode. So now we are discussing about the PN junction photodiode only. Still now we are discussing about the PN junction photodiode. That means P region and N region. So due to that P region and N region, what happened? So in between some depulsion layer will be formed. So the depulsion layer, when light is instant on the depulsion layer, so charge carriers will be developed. Due to that charge carriers, current is passing through the circuit. This circuit is connected in reverse bias. Okay, this is about the PN junction photodiode. Okay. Now coming to the PIN photodiode. So there is some disadvantages in PN junction photodiode. To overcome the disadvantages, So PIN photodiode is made. Okay, so how to overcome? So first of all, see here. So what is the PIN? We will discuss. P means positive, I means intrinsic, N means negative. So PIN diode means so positive intrinsic negative diode. Positive intrinsic negative diode. Okay, so is a device that consists of P and N regions separated by a very lightly doped intrinsic region. That is, the intrinsic region is I. Okay, so that means here, so positive means P region and negative means N region. That positive and negative region is separated by another intrinsic. Intrinsic means so pure semiconductor. Pure semiconductor, that is intrinsic region. Okay, so in between, so P-type semiconductor and N-type semiconductor. So there is a in middle there is a intrinsic lightly doped intrinsic region will be there. Lightly doped intrinsic region will be there. So this is the construction of PIN diode. So why we are taking like this means, so for increasing the area of the depulsion region. Observe here. In between so P region and N region, so there will be an intrinsic region will be there, as well as due to that P and N region, there will be a depulsion layer will be formed. Okay, so now depulsion, width of the depulsion layer is so high. Width of the depulsion layer is so high because in between depulsion layer will be there. So and because of P and N region, some depulsion layer will be formed. Okay, so that's why width of the depulsion layer will be so very high. So that's why, so what happened, so maximum, so we can very high intensity also so absorbed by this material PIN photodiode. Very high intensity of the light also absorbed by PIN photodiode. Okay, so because so that depulsion layer only absorbs the photons here. So that's why if you increase the width of the depulsion layer, so this we will overcome these all disadvantages. We will overcome these are all disadvantages here. Okay, so we will discuss this PIN diode in next class. Okay.